Okay, so here we have the ArcOmeter. I recently taught a class in 3D printing, and one of the things I asked the students to do was to bring in kind of a capstone project where they could walk through the entire workflow of 3D printing, including designing a part, slicing it, sending it to the printer, printing it, doing the post-printing processing, and then installing and using it. And one of the students brought in a perfect project where she had a pot, cooking pot, and the handle broke. Um, so so she designed and printed the part, and it works fine. But the bottom of the handle was flat, and the top of the pot was curved, and so you can see there's like a little gap here all the way around it, and it still works okay. But I thought, it would be cool if you could design the pot lid handle so that it would have a convex face like this, so it would fit the contour of the lid, and you see, a curve here like this. But the question is, how would you measure the radius of the arc so that you could model it accurately? Well, the answer is you can do what's called a saggitta calculation. And the way it works is if you draw a chord across a circle and then measure the height of that chord, you can calculate the radius of the circle. And so what you end up with is a right triangle right here. So the horizontal leg of the triangle is the chord length divided by 2. The height of the triangle is the radius of the circle minus the chord height, and the hypotenuse of the triangle is the radius of the circle. So you plug all that into Pythagorean theorem and then do the algebra, and what you end up with is a formula for the radius as a function of the chord height or the saggitta. So I designed the ArcOmeter to do this, and at the heart of the ArcOmeter is a linear potentiometer, kind of like the faders that you'd see on a audio mixing board, and then attached to that is a probe that comes out and touches the part between 2 points that form a chord. So with the front end of the thing here, you can calculate what that chord height is. And then I've got a microcontroller that reads the position of this linear potentiometer and then calculates the arc length, and sends it to an OLED display here. I designed and printed a board to hold everything, and I power the thing with a LiPo battery. So I also designed a calibration block, and it's simply a series of arcs. So the shortest one has a radius of 60 millimeters, and the largest one has a radius of 120 millimeters. And I use that just to get some values. And so all you do is you take the ArcOMeter and you bring it up to one of the curves to where the points of the probe touch, and the cord touches, and then the probe touches the part. The measurement circuit is just a simple voltage divider. So I've got a 1K resistor in series with a 10K linear potentiometer. So I got 3 volts coming in the top here, ground at the bottom, and then the wiper of the potentiometer goes to an analog input pin that can read the value of the potentiometer, and then just a 32U based microcontroller. The software is pretty simple. There's some setup where I import some libraries, create an instance of the display, start the display, and then set up the display with the text size and color. And then in the loop of the program, just a real simple thing, perform an analog read to get a sensor value. And then I calculate the arc length, and I'll show you how to do that in a minute. And then take that arc length and display it. So it's just a matter of setting the cursor position, putting in some text, and then displaying the arc value. So the way I do the calculation or the calibration is I start at the top here, and I get a reading from the sensor. And so the program that I wrote has some provisions in it for a serial monitor. So when it touches the top here, I got a sensor value of 339. That's on the 120 millimeter arc. And then on the 60 millimeter arc, I get a sensor value of 228. So now it's a linear relationship. So I just put that into a little spreadsheet here. And so the equation is in the form of y equals mx plus b. And so you calculate delta y and delta x and then divide those two to get the slope of the curve. And then you plug in one of the x and y pairs to calculate b. And so what you end up with is a formula that says the arc length, or the radius of the circle, equals 0.54 times the sensor reading minus 63. And so you put that into the program, and it works. So there you go, the ArcOmeter. So if you've got any arcs you need to measure, let me know, and we'll get together and we'll do some measurement. All right, there you go, ArcOmeter.